All right, here we go. So we're going to talk about these ionic solids today. These do come into play with Coulomb's law here. The ionic solids then are going to have these cations. Remember, cations have a positive charge. Meow. No?
That was fine, but the meow was
a little over the top?
Yeah.
All right. Anions are going to have a negative charge. I kind of think of those as like antagonists in a novel. They're the negative people, you know.
I'm a positive fairy.
So we'll just nickname you anion. So discrete ionic molecules do not exist. Instead, it's a repeating array of molecules that are held together by Coulombic forces between the oppositely charged ions. So oftentimes this is called a crystalline or a lattice structure. A lattice structure, right? Kind of like my initials, yeah. So ionic solids are non-volatile. What does that mean? Volatility, if something's volatile. Do we remember back to our IMF discussions last spring? Okay. So non-volatile, remember, and one of the reasons why they're non-volatile is because to be volatile, you need to be in a liquid state, okay? These are tending to be in a solid state at room temperature, okay, because they have high melting points. Now, if we talk about the term volatility, okay, remember what volatility is if you have a sealed container. So here's my little flask, and I have a liquid in there. Remember, those liquid molecules are able to kind of move back and forth. Well, some of those molecules down here are changing into gas molecules. And they're coming back and forth. They're just kind of repeating. Some of them are liquid, some of them are gas, and they keep moving back and forth. If you have a volatile substance, that means that you have low IMFs, intermolecular forces, which allow more of this liquid to become a gas. So substances that tend to have high volatility then will have more gas molecules up here. That exerts pressure. So that's one of the impacts of this. It produces pressure on the system. This is why when you buy a gas can, if you've got a gas can that you have at the house for your lawnmower, there's always a little valve back here that has a hole in it. Okay, because gasoline, you should have a red gas can.
No,
gas should be gas. In.
I'm saying my lawnmower is green.
Oh, okay. So, at any rate, have you experienced that gas can? Do you know what I'm talking about? There's always a little stem valve back here, and it has a little hole in it. That's to let some of those gas particles escape so that you're not building up too much pressure in there. It tends to be that things that are high in volatility are also flammable, but one doesn't cause the other. They happen to kind of come together. But the fact that, you can have things with high volatility that are not flammable, but typically your flammable things are going to be highly volatile. Okay, so this will come into IMF discussion. I believe that is unit 3 when we get back into that, but that's kind of the idea behind all of that. Okay. All right. Where was I at here? Okay, so when we're looking at ionic compounds, then high melting points, they tend to be always solids at room temperature. Ionic bonds must be broken to melt those solids, which will separate into oppositely charged particles. That's going to require very high temperatures. I don't have Bunsen burners that are able to get to that high temperature. Ionic solids do not conduct electricity. The charged ions are fixed in place. So they're in this lattice structure here. And because of that, they can't slide past one another. But if you melt them, then the individual ions are able to move. And then you can have conduction of electricity. Or if you dissolve them in a solution. And some of these you can dissolve in water, and some you actually have to dissolve in something else to get them to work. Okay. Once they are dissolved, though, then they can flow and conduct electricity. Many ionic compounds are soluble in polar solvents like water and insoluble in nonpolar substances like benzene. Relative strength of different ionic bonds can be estimated by using Coulomb's law. It states that the force is proportional to each of the charges and inversely proportional to the distance squared. So calcium oxide, we have 2 plus and 2 minus. That's going to be a much stronger bond than NaCl, because these, you're only going to have a +1 and a -1. And if you look at the boiling points, you can see that this has a much higher boiling point than this. We can also look at these distances, okay? So if we compare, for example, sodium chloride versus sodium bromide, these are going to be closer together than these. This is higher up on the periodic table, so it has a smaller radius than the bromine. Again, you can look at the melting points and see that that's indicated there. Okay. Questions on any of that? All right. So why does KBr have a higher lattice energy than Ki? Less distance. Yep. Yep. Stronger force of attraction. Okay. And then draw a diagram of rubidium iodide. Be sure to include relative sizes. So rubidium is, RB is number 37. So that's RB. And iodine is over here. Which is going to be bigger, RB or iodine? Okay, this is going to be plus. It will have lost an electron, right? So it's going to be a plus charge. Iodine will have done what? Gained an electron.
Okay. Oh, that.
Okay, there, everyone. So which one of these is going to be smaller? RB, because it will have lost an electron. So it's going to have a higher effective nuclear charge. So compared to what our RB would look like, the plus version is going to be it's going to be smaller. So this is going to be RB plus. And then we're going to have iodine coming in. Okay. Iodine's larger than I because remember with this guy, once he's become a plus, what electron configuration does he have? Noble gas. So he has the electron configuration of krypton. So he's lost a whole valence shell there. So instead of 5 valence shells, he's only got 4. Okay. So he's going to be significantly smaller than the iodine.
I don't like that erasing. Because like that new, I don't like a new board and it's usually kind of weird.
Well, this is my old setup. I just brought in my my computer from home because I wasn't confident that I was going to be able to use that thing today. And because there's a little bit of a learning curve on it. And so I knew that I had been told that I could just hook my computer up to it through this cable and then I would be okay. And so I knew that I could fly with you guys today and not have to try to figure that thing out while I was trying to teach a class. I can't do all of that on my own. It just, right now, I can't handle it all. All right, so RB is going to be smaller. So I'm going to do RB plus. I'm going to do that as a solid circle, okay? And iodine minus, I'm going to do as a circle like this. So I'm going to have one of these, and then I'm going to have an iodine. And then I'm going to have one of these, and I'm going to have an iodine. And then it's going to alternate.
Okay.
Okay, so that's what that looks like.
Okay.
Questions on 2, 3?
How do we know to draw it?
Oh,
okay. I got it.
Is that like as much as we need to draw of it?
Yeah, that'd be fine.
Genius.
Typically, a lot of times they will say, like on a test, make sure to draw 8 ions. You know, make sure to include 20 ions. Okay, so they will tell you specifically how many. Otherwise, here you kind of get you get the gist of this, right? I mean, we could keep going with this, but you kind of get the gist. They can see that you've changed the size of it. They can see that you have it alternating. That's what they're looking for. All right. 2, 4 then is metals and alloys. All right. So there's a couple things that you need to know about these. Remember that these are composed of cations. They also have delocalized C of valence electrons.
What does that mean?
That means that, you know how it's almost like they have electrons assigned, like when we do the molecular structure, it's almost like we have electrons assigned to like carbon, for example, okay? And you can kind of visualize those as being there. With metals, like you don't know if that electron's from that guy or that guy. They're just, it's like free love, baby, in the 60s. You know, they just kind of move and they flow and they, yeah. And the beauty behind this, though, is that this can be a solid at room temperature, and moving electrons is what? Electricity. Yeah. So we can use that ability of these electrons to flow through here and harness it as electricity. So it's like these electrons are just the free loving, like 1960s hippies. Yeah, they're just like, go with the flow, man. Let's go. Yeah. That was before my time, you guys. I wasn't born then, by the way. I am not that.
72.
71.
Oh, yeah, because of the baby thing. We talked about the vaccinations.
Yep, polio. Or not polio, smallpox.
Yes.
Smallpox, yep. So kids that were born in like 71 we were like the last people to get smallpox vaccinations. My cousin was born in 72. She doesn't have one.
My father doesn't.
So that's like the cutoff was kind of my generation. So.
Oh, wait, don't.
All right, anyway.
I don't want to get.
So you can't tell which electron came from which cation. So that's the idea behind this concept of delocalization. They're just kind of flowing, they're moving through. The number of valence electrons then determines the amount of electrons in the delocalized sea of electrons. When the charge on the cation and number of electrons increases, the attractions are greater. And additionally, when the atomic radius decreases, that's greater as well. So here, when we have a +2, you're going to have more electrons flowing through. So this is what we're talking about with like group 2 metals versus group 1. So these are your alkaline metals that you actually have alkaline batteries. And it's preferable to have alkaline batteries versus alkali batteries because you're going to have more electrons to move.
Okay. More.
All right. We also have stuff called alloys. And what an alloy is they have taken two different metals or two different substances. They will heat that substance up, that metal. They're going to get it to go into a liquid state, and then they introduce another element in. They can introduce a very small element in that fits into these holes. These holes are called interstices, and when they cool this back down, those little atoms fill in those holes. What does that do for the structure of this material? Makes it stronger. This is what steel is. So when you have steel, you're able to build big, huge skyscrapers and bridges and all. This right here was one of the leading reasons that the Industrial Revolution actually happened. If it wasn't for steel, it would have never gotten off the ground, because they needed to be able to have those bigger machines, to be able to do the assembly lines, to do the stuff that they did back in the Industrial Revolution. You know, your trains, all of your freight, that sort of thing. Those are steel cars a lot of times that do that. Your big bridges that span over the Mississippi River and stuff like that, transportation. Before that, you know, they were building it out of wood. You can't put that much weight on wood. It just won't support it. So this was one of the leading things in the Industrial Revolution. We could also have substitutional alloys like brass, for example, where we have copper. Copper and nickel is not brass. Copper and zinc is brass. Yeah. But the size of this atom and the size of this atom are fairly close to one another, and they just end up subbing in. So there would have been a gray one here that gets kicked out to over here, and this guy comes in. Okay, so this ends up giving it certain properties of both metals and gives you certain benefits. So it might reduce corrosion. It might strengthen it. So bronze, for example, there was a whole age back in history that was named after that alloy, the Bronze Age. Okay? I'd have to look it up. I don't remember. Copper and nickel. So this probably was bronze that we were talking about right here. This is probably bronze right here. I know copper and zinc is brass because we've done a lab before where we coat a penny in zinc and then heat it in the Bunsen burner, and it makes it look, it's brass. Then you take the copper from the penny and the zinc come together and they form brass. It ends up being a gold penny in the end.
Really?
Mm-hmm.
Wow.
Gold in appearance, gold colored.
Yeah.
All right. Carbon steel is an alloy composed of small amount of carbon atoms combined with iron. Consider the atomic radii of carbon and iron and draw a model that describes the alloy that forms. So there's your model. You can see where we've got the carbon fits snugly down in here. Then down here, examine the diagrams below, then label with each type of substance. So what is this? It's just a metal, yeah. A pure metal, I guess we would say pure. What is this? Substitutional alloy. And this is an interstitial alloy.
Okay.
All right. So that is it for today.